Hello and welcome to this next session on our agent-based modeling tutorial using Julia and Agents.jl. In the last video, we stopped after introducing the R state from the SIRS model. And in this new session, we'll think about information and how people will communicate about their knowledge about a disease. And in this case, we would have something that we would call awareness. And we'll take the term awareness because there is a famous, or at least a researched model that is called the UAU, and I'll put it in a comment here, UAU-SIS model. And that means we have a model that is an SIS model, and we have a UAU model, which means unaware, aware, and then people become unaware again. In this case, we would say 0 is unaware and 1 is aware. And if people are aware of the disease, they're going to protect themselves. And how will this play out? First of all, we need to determine something like what is awareness for a person. A person will become aware if they hear of an infectious event in their immediate neighborhood. So one thing that we could do is in the agent step function, independent of the person's state, and for this, we would copy this here because awareness is not triggered depending on whether you're healthy or not, but it's triggered in general. And then we would say if the neighbor's health is at 1, so if that neighbor is infected, but we shouldn't do it like during this, no, that doesn't make sense. Let's throw this away. We don't want to update the information during the state of infection, but we want to update it when there happens an infection, because that's when you tell people I'm ill, and that's when they change their awareness. And one thing we could do is, in this case, as soon as a person, if one of the neighbors is infected and you become infected, you should let all the neighbors of that person, they should get the information. So what we would do here is for our new neighbors, these are the neighbors of the person that got infected, in nearby agents of that neighbor, of that person, dot model. Wait, isn't that the same? If that person, actually we can let every neighbor know, but we have to do that again because, yeah, we'll put it here. So for every new neighbor, we can then update their awareness. So we will let that new neighbor dot awareness, that will become 1. So that person, every person in the neighborhood has now been informed about the disease. As soon as you get an infection, you let everyone know around you. That is a very simple assumption. The challenge now is, what does this do? If we have awareness, do people change their behavior? And there's multiple ways of doing this. We could say that the awareness reduces the susceptibility of that person. So in this case, we could have a look at the awareness, and if it's 0, it's unaware, and if it's 1, it is aware. So let's first keep note of inform the neighbors of infection event. But even before this infection happened, we should consider that the awareness might reduce this. So how could we reduce the model susceptibility? We could do something like we multiply the model susceptibility, because it should become smaller. We should multiply it with something like 1 divided by 1 plus person awareness. So what does this do? And we should put this here in parentheses. what we do if we do it like this is we have a model susceptibility, but this model susceptibility is transformed by 1/1 plus person awareness. So if person awareness is 0, which is they're not aware, then we divide 1/1, so it doesn't affect the susceptibility, so the person is as susceptible as they were. But if the person is aware, then this becomes 1 plus 1, then we multiply the susceptibility by 1/2, so we reduce the model susceptibility to half before actually applying it. So knowing of the disease reduces your risk of infection in the next steps by half. And the question is, if we have a look at what's going on here, we should probably also in the plot say something like aware of P. So we test for that. P dot awareness equals 1 and unaware of P is equal to P dot awareness equals to 0. So these are things that we can then plot as well in our model, and we would do this maybe here by counting them as well. Let's put it like this. We could then put aware, comma, count, and unaware, comma, count. And then we would see not only the amount of aware, but also the amount of unaware people. And we have an error. Invalid redefinition of constant person. Yeah, this is if we change something without restarting Julia. And now we can have a look at how awareness reduces the amount of infections that people have if no method matching. Oh yeah, that's an interesting thing. Once we change the model, we obviously have to initialize our model in a way that we make everyone unaware. So here the person now has another value, which is the awareness, which is another in64. So that makes more sense. And let's see if it works now. We should probably check if the other videos and figures, if they also make sense now. But I think they should. We can quickly check while it's calculating. This does not look at awareness or anything in that regard. This doesn't either. The param scan doesn't really look at the data at all. So yeah, that should work. Is it still, it's activating? Yeah, okay, we still have to wait. And it's done. So there should be our Julia code here. And this is now also keeping track of the infected, the susceptible, the aware, and the unaware. And as soon as we start running this model, oh, there was an influx immediately. We see that people become aware until everyone is aware. But the awareness doesn't change that there's no infections happening. It just decreases the spread by half. So the infected, the speed of how fast people become infected should be reduced. And now we're seeing some, let's increase the speed even further, and we now see waves. And the distance between the waves now depends on this very rare random event of a new infection coming in. And in this case, yeah, we will see wave after wave after wave, but they're not as predictable as they were before because they highly depend on the influx. But the awareness now stays forever, and that is not a UAU model, it's just a UA model. And if we really want to have a UAU model, the awareness should also diminish over time. And one way of doing this is to have an awareness duration. So we add in our initialize function an aware, let's say model awareness duration, and that is how long are people informed about the disease, and we can put in a default of maybe let's do twice the time as the illness, and they forget soon afterwards. But we also have to keep track of that for the individual agent awareness duration, which should also be an in64. How long has the agent known about the disease. And what we can also try to do with that is we have to factor this in here as a parameter, and let's put it here with the model parameters, and let's say model awareness duration, and that is only we have to tell the agent that they have a 0 awareness in a duration in the beginning. And since we're doing awareness here in the beginning, we should probably also update it here. So if update awareness, if person dot awareness is equal to 1, awareness. Interestingly, what we do here is something that we do in the plotting function as well. So these functions, which we could call something like these are predicates. Let's remove them from here because they are not strictly related to plotting. They are actually more related to the model and actually to the agent, because what they do is they evaluate a person and they provide an easy to use function, and it makes this utilizing these, we call them predicates of our agent. And we could even do something like this here. We tell the tool that we're only using this for persons and not just for any possible P, and not for PPs. Now, as we have these, we can utilize them by, instead of saying if person awareness is 1, we can only say if aware person, and then this only happens if the person is aware. And the same we could do here if susceptible person, then we would have a susceptible person. So if the person is aware, we should person dot awareness duration should increase by 1. And if that person's awareness duration, person dot awareness duration, if that is greater or equal than the model awareness duration, so the awareness expires, that person's awareness should go back to 0. So they will forget about the disease, and the awareness duration should also go back to 0. So update the awareness, and if person forgets, we forget about the awareness. And if we now run all of this, we cannot redefine the constant person because we have to restart the Julia console. So one thing to keep in mind is when you're changing your data type, you will have to wait a little bit longer before everything is re-rendered. So let's open this up. As soon as we're there, we're there. And if we now run the model, we should see that people become aware, and then they also become unaware again. And since the dates are kind of correlated, we now see that there is these two waves, the infection waves and the awareness waves, and they're kind of connected to one another because you become aware as soon as someone else becomes infected. And the question is that how awareness works? In this case, you can either be aware or not, and you forget about it completely. But if you remember, in reality, that's not how things work. You kind of tend to forget over time. So although we just re-rendered or reloaded all of our function, one interesting way of doing this would be if the awareness, instead of an integer, would be a float. And a float is a floating point number. And from this, we would say the person awareness, a person is aware if the awareness is maybe greater or equal than 0, they have at least some awareness, and they are unaware if they don't have any awareness. So in this case, we would see if a person is aware, the duration increases. But here we would not say the awareness after the duration goes down to 0, but it reduces it by a certain amount. And we could even do, we just forget half of what we know every awareness duration. So it's kind of like it has a half-life of awareness duration, and this will reduce it to a certain amount. The problem with halving is that you will never actually get to 0. And we will see what that means if we run the model. I think it should work like this. We have to restart Julia, obviously, because we changed our person. And let's see if we get a visualization here. There it is. And let's make this larger again. Here's our infected person, and we run the model, increase the speed, and we see that everyone is aware because greater or equal, okay, that doesn't make sense. The unaware disappear. This one doesn't make sense because greater or equal is not correct. And so let's remove all of this. And let's go again and check where did we define this in the model. We have this here, greater or equal is, doesn't make sense because people are only aware if this is greater than 0. And then if we run all of this again, we should quickly see, yeah, there it is. Run the model, and we should improve this or increase the speed. We see that people become aware, and they will stay aware, and they will quite literally stay aware forever. Not because it takes forever for the awareness to disappear, but the individual awareness of an agent, it just never reduces to full 0. It only goes to a very low value, and that makes sense in a certain way. But we should probably, instead of going down to 0, we should define awareness as above like 10% of knowledge. Anything below 10% does not do anything. And we should also, in the behavior, check that if that person is aware, I mean, yeah, that should still work. So what happens now is if a person is aware, when we verify this, if it's greater than 0.0, we will increase it. We increase the awareness duration, and then we halve it. And as soon as they're no longer aware, we're no longer halving it, and we're also reducing the awareness duration to 0. And the awareness is changed here to 1 whenever an infection happens, so we don't, this should still work. And did it, oh, it already finished, so we can now, we should be able to see it. If we run the model, increase the speed, we see that we have more people becoming aware, and then people becoming unaware. But they're becoming aware again because they're reinformed depending on the amount of infections that were ongoing. So here we have a series of awareness because there were lots of infections happening. Interestingly, the unaware doesn't work anymore because in the model, oh, I closed the model, I didn't want to do that, because the unaware should obviously also say, and then here maybe it makes sense to do greater or equal because that makes sense, and here we would have less than 0.1. And we could have this threshold as a model function. Then we would have to export these functions. They would need a model to determine the awareness, and from the model they would so just to explain what I mean, we could also have a function that goes p double person, and we also get a model, and this would then say equal p dot awareness is greater or equal than model dot awareness threshold, so to say. But then whenever we call aware, we also have to supply the model, and that ruins the plotting for us. So we just keep it as is, and if we really want to change it, then we have to think about how to do that. Now it should work, and we should now also see that the unawareness will go up again over time, because people are, so these should now be opposites. As soon as this goes down, this should go up. And we now see that we have complex waves of infections going on. We don't see who is aware because we haven't colored it. We could add different shapes for that, but at the moment I think, yeah, if we increase it to the size, we could also make the size depend on the awareness. Function person shape of a person, if p dot awareness is greater or equal than 0.0, and we haven't defined this yet, obviously, then return. So people that are aware, they should maybe become a circle, circ, else return rectangle. But the rectangle, I think we write it like this. And we now have to supply the person's shape in the interactive thing here, where we, instead of am rect, we just give it a function person shape. And we could reduce the size to 20 and see if we now do all of this. It should be relatively fast because we didn't change the agent. We can now, if we make it large enough, see that the aware ones will turn into circles. No, we don't, because circ using unsupported marker, using, isn't it circ? What's it called? Circle. It's not circ, it's circle. Model, plotting, not circ, but circle. But rect is possible, I think. So let's do that again. And let's go back here. And now if we run the model, we can now also see how awareness kind of spreads around these individuals, because some of them now turn into circles. It could be that this reduces the rendering speed. I'm not so sure why this is happening. It could also be a different problem. Let's see if I close it. And if I restart Julia again and run all of this, AM is person shape, yeah. And this will now take again a few seconds. And we should now be able to see if this still is very slow. Run the model. It seems to make everything relatively slow if I have this in here. I'm not really sure why. Oh, that is slow, obviously. Okay, let's see if the person shape in the plotting function, do we do something that might be, I mean, we do another check for a variable, which is a floating point comparison. We could also just do end and in general return rect. If p awareness is larger than, we could also say if aware p that should be much easier. Let's see if that works. Now that this should load fast. Interesting. I didn't know that. I did not know that having two types of shapes has such a big impact on plotting. And we could try very easily by doing rect. Maybe drawing a circle takes long. I don't know. Let's see if I do the rectangle alone, if that's also slow. Run the model. That is not slow. Is doing circle, is that slow? Because drawing a circle is more math complicated than drawing a square. Run model. Not really. It's not about the circles or the squares. So it's about having a function in here. The marker, if that has a function, and the function is called person shape. And in this case, it does something, but we could also very quickly test if we do this. So this is unreachable code. It will always return rect. If this causes the problem, run model. It's already a lot slower. And it does not react well to interactions. Interesting. So having two functions in here makes it a lot slower. So maybe instead of doing that, we should do rect and try not to only visualize awareness for smaller models. I'm not really sure why this is happening. I would have assumed that calling a very simple function such as person shape should not be a problem. I'm wondering if the signature causes a problem. If I turn this into a person, if this will also be slow, because that would be an easy fix. Run the model, make it fast. No, that's the problem. It is calling an additional function, and I didn't know that. I was unsure that calling person, I mean, it's obvious that this has to be called 10,000 times on the person, so it obviously creates a lot of overhead. But in this case, it would also mean that the simulation, if we draw the colors, it also takes quite some time. I'm wondering if it is fast because we only compare integers against 3 values. That could be the reason. So my recommendation is not to use both the marker and the color if you're using a larger model such as this one. Okay, this concludes our video on adding awareness to our model. So we now have a UAU-SI model. As an exercise for yourself, you could try to add the awareness duration into the parameters of the interactive model and see if you are able to add these in these sliders in for the awareness duration and see how the awareness duration affects the spread of the disease in your model. One thing that at the moment is a little unsettling or not very satisfactory is that we randomly introduce influx from the outside by this very small probability. Obviously, in a regular simulation, you would probably have a simulation of the outside world, and the more people are infected in the outside world, the more likely it is that you will have an influx of infections. And that is something that we're going to look at in the next video. But this is it for today. I hope you enjoyed this tutorial, and I'll see you in the next one.